Wireless HD. So this is a competing standard which actually started much earlier, and it was the favorite standard at one particular time in 2009 or so, 6 years ago. And a number of wireless HD products that started coming up, but now they're all going away in favor of 11AD. So this standard is same, 60 gigahertz for DVDs and DVRs, and designed for high quality uncompressed video. This was the justification. And as we said last class, maybe this is more of a theoretical justification, because in practice nobody watches uncompressed video. We are all happy with the compression, and so this might be done in the studios. With this you can do lossless 3D, 48-bit color, 240 Hz refresh, 4K resolution, everything at the extremes. I don't know how many of us have this kind of TV. So these are all available in the market today. You can buy 4K TV very easily. You can buy 240 Hz refresh. 3D is there, but I don't know, our 48-bit color, maybe it is there too. So all of these features are available, not in one TV, but maybe in different TVs. And so you can create what they call wireless video area network, WWAN, video area network. So they had personal area network, local area networks, and so on. So now we have video area network. And as before, they use 4 channels of 1.76 gigahertz, which is exactly the same as 11AD because it's the same FCC spectrum. And they use, they can get very high rate, and they can also do non-line of sight, okay, most likely through the relays, okay. So everything that was in wireless HD actually has been taken over by 11AD. So some of the features that we will talk about in wireless HD, since it is older, there is no reason for somebody coming later not to use the best of the past. Okay, so if there is any good feature in wireless HD, this is probably already discussed in 11AD. So they have 3 PHYs: high rate, medium rate, and low rate. And the reason is exactly the cost. Because if everybody was designed for gigabits and they didn't need gigabit, the cost could be high. So they said, okay, all right, we will have some low cost station, medium cost station, and high cost station. High rate will do up to 7 gigabits, medium up to 2 gigabits, and small up to 40 megabits. And so these names you should remember: HRP, MRP, and LRP. Low rate PHY, medium rate PHY, high rate PHY. And these two, HRP and MRP, they are noted by HMRP, high and medium rate PHYs. And LRPs, they use the same band and use TDMA. So you know what that means is that they will do time division multiple access if they're at the same place. Peer-to-peer, no access point, need one coordinator. And so this is actually a kind of thing which we will see from many different ones that we have seen in 11AD already, and we will see in Bluetooth and other places where they will say it is P2P. So there's no one which needs, there's no access point as required, but access point still is a function which might be implemented inside the station. So same thing here, you need a coordinator, and the coordinator is not a separate box, it is built into the station. A device may have a coordinator capability. Generally, displays and storage devices have this capability. So what this means is if you have a TV, which is a display device, and it costs a few $1,000, and if you put the PCP function inside there, nobody will notice it. And similarly, storage, they are saying storage devices could be a router with some storage. They will not notice it. So the Mac, So the MAC has basically the coordinator function as we saw in 11AD. And everyone can transmit and receive LRP, but some stations may do HMRP. So this is minimum required, and everyone should be able to do low rate. Okay, this is similar to the band. What do we call channel bonding? In channel bonding, we have primary channels which everybody listens to, and then if there is an extension, then some people can do the extension, and some people may not do the extension. Similarly, LRP is the minimum required. Shut down and sleep modes as usual. Channel estimation. Everybody knows what is channel estimation mean by now? Huh? You know what is channel estimation mean?
We should know. Yes.
You know, yeah. But okay. Channel estimation means basically measuring the channel, right? Quality of the channel, how good it is. So that is now common, is starting from, I think, even from 11N and other places, right? Higher layer, so basically MAC does this video format selection, video coding, encoding, service discovery, etc., etc. So there are some functions at the media access layer that are related to video here, which actually would call application layer, but they're all there in wireless MAC, wireless HD MAC. But what I really wanted to discuss, and the reason I'm putting wireless HD in this lecture, is the OFDM part. And here is the table of the OFDM parameter for wireless HD. Similar tables are there for everything that uses OFDM. Actually, there is a similar table for 11N. Actually, OFDM started with A, G, N, AC, and it will continue in WiMAX, LTE, LTE advanced, everywhere, right? So all of these have a table like this. So I wanted to explain this table, and you should be able to read these tables from now on after we finish this. So that's why I'm presenting wireless HD, because this is the first time when this table appeared. So there are several parameters which are specified when you specify an OFDM network. First, there are some parameters which we can call frequency domain parameters, some which we can call time domain parameters, and some which we can call coding parameters. And I will go through slide by slide through each of them. For frequency domain, just notice these parameters. We start with the occupied bandwidth, subcarrier spacing, and so on. So let's go to the next slide. So what you first decide is how much bandwidth can you get. So we get total 1.76 gigahertz from here to there. Then the question is how many subcarriers we will have. And so in this case, we decided that the spacing is 4.957 megahertz. All right, so that is the subcarrier spacing. That will give you how many subcarriers will you have. So with 1.76 divided by 4.957, you will get about 355. Yeah.
The previous slide, I just wanted to clarify something. Is FFT period the same thing as FFT duration?
FFT rate is the same. Huh?
FFT period, is that the same thing?
In this slide?
Yeah.
FFT period is same as the FFT duration.
Yeah.
When we come to that, we can discuss about that. I mean, where did I use FFT duration?
Oh, I mean, it was in homework 7, that's all.
In homework 7.
Yeah,
we haven't gotten there yet. Okay, all right. When we get there, we'll get there. Okay. So here we are now going to talk about time. In this slide, we are talking about the frequency so far. The next slide will be time domain. So here, all we are given is 1.76 gigahertz, and we decided that we will use the spacing of this. So we get number of subcarriers 355. Of course, the FFT size will be 512 because we know that, right? Power of 2. So the number of data subcarriers out of 355, now we have to divide that into several different kinds. And we have discussed that too in the past, but now just to be more clear, 336 will carry the data which are shown in black. Three? Huh?
The others are only for pilot project?
No. So there is more. So there are 3 DC subcarriers. So there are these 3 in the middle, which are really direct current, which means that they don't have any frequency, I mean, as such, right? But those are basically gaps, which are used really for frequency synchronization of some kind. So I've seen this, DCs in all the other standards that we'll see in the center. So these 3 in the center are the DC subcarriers. 16 are pilots, which are shown in red. And then at the end, there are 157, which is actually, these are nulls. So we are not even using them, 157. They are similar to DC, but they're not called DC. So I don't really know the difference between null and DC, but there is some direct current here in the sense that there is some voltage, things like that. But how do you send the voltage on the air? I'm not sure. So these are DC and these are nulls. So if you add up 336, 3 and 16, you will get 355. These are there. And these are just null subcarriers. We can call them guard bands or whatever. So these are not used here at the end. Yeah.
The number of pilots and DC subcarriers standard, or can you infer from the bandwidth?
Okay. So this is a standard for this standard. I mean, this is the number that you will use if you do wireless HD. Every standard has, so in this case, for example, they selected that out of 336, we will use 16, which is like every 21 or so carriers, there is a pilot, right? Now, depending upon how far it is going, if you're going very far, you probably want more estimation, better estimation, then you will do more pilots. Since this is short distance, they selected this number. So these numbers are all kind of, argued, discussed, simulated, analyzed during the standard for basically writing. And the results are presented. So this is now this number of pilots for this number of data carriers is for this standard only. It may not apply, for example, to 1180. They might have some different number. Yeah.
What is the usage of these subcarriers?
User?
I mean, what's the advantages of that?
DC. Yeah. So my understanding is that the DC is, now I will have to correct this, when I come back next time. DC is more for placing the frequency band, basically recognizing where the frequency band is. So, but how do they do that with DC? So I have to kind of, figure out more as to what is the function of DC and how it is different from null. Null means no signal. DC means direct current, right? So how does DC go through? But there are 3 carriers in the middle which are DC, and then we have pilots and data, and then at the end we have null. So these are the frequency parameters. Any question about the frequency parameters?
Why do we need null subcarriers?
Null carriers?
Yeah.
Oh yeah, because you see 512 is the number FFT size. So basically what will happen is you get 336 plus this numbers, you get about 355. If you have a matrix which is 512 by 512, right? These 157 would be zeros. So when you do FFT, you have these matrices. You invert and multiply and this and that, right? And this is a matrix which is 512 by 512, right? Out of them, only 355 columns and rows are being used. The rest of 1757 are zeros, and that's what these null carriers represent. So in diagram form, what we are showing here is that there are 70 some number here, 78 or so on this side, 78 on this side. These are null subcarriers which are not there. Does it make sense? Okay. In mathematics, there are zeros in the matrix, in the calculation, right? But we are not using that part of the band. Now, a similar table will exist for MRP and LRP. This is for HRP, high rate PHY. A different table. So, for example, if I were to present MRP table, it could have a different number of pilots because now the rate is lower, so you don't need that much accuracy in estimation. The next thing they specify, is the mask. So every standard has a frequency mask. And so what is frequency mask? Basically, on the x-axis we have frequency. On the y-axis we have the power that you can transmit. So at the central frequency, you can transmit whatever power you can transmit. And that number is given by FCC, maximum power transmitted. We call it 0 dBr. Here dBr, R simply means relative. So let's say you decided that the maximum power allowed by FCC is, if I remember correctly, it was 23 or some number dBm, right? 33 dBm with everything else, EIRP and all that. So that would be 0 dBr. Right? That is the baseline. Okay. Minus 20 dBr means 20 dB below that number. Then you have to come down. Basically, at 1.1 gigahertz above the central frequency, you have to come down by minus 20 dB. Okay. So let's see here. So up to 0.94, you can have full power. Between 94 central frequency plus 0.94 gigahertz to central frequency plus 1.1 gigahertz, you will come down in power like that. And then after that, it will be even less, and so on and so forth. Okay. So you can see that even though the band given to you is only 1.76, which really is somewhere here. 1.76 is somewhere here. It is 1.88 right there. So basically what happens is, generally I would have expected that this would be 1.76 right in the center. This much. But this is more than 1.76. So this rest of it is overflowing into the neighboring channel. All right. And so you try to minimize the neighboring channel overflow. And that is done by specifying that you cannot be more than this amount, So by this time, you have to be minus 30 dBr. And minus 30 means 1,000 times. Minus 20 means 100 times. And so on. Right? 20 dBr is 100th in non-log scale. All right? So they specify a mask like this, and when they design it, basically what happens is, even though subcarrier is just, we show like a straight line here, impulse. Subcarrier is not an impulse. Actually, what is a subcarrier is a square wave of some kind, and therefore it has a frequency spectrum, okay, which overflows, except that it is designed such that the power is 0 at the next subcarrier. Okay, actually I might have a picture. I tried to draw a picture. Right here is the picture actually, which explains that. So let me explain this. So the subcarrier, even though we show it as an impulse, it's not an impulse. What it is, it's a square wave. Okay, a square wave in time has a frequency spectrum like this. Okay, where there is a peak and then the period is 1 upon t. I mean, of this wave, it's not it's a sine wave, so there's a frequency, but at 1 upon t, it is 0, and then Again, it is 0 like this, and it slowly dies down. So when we do OFDM, what we are doing is we are putting shapes like this. I haven't put it. You put many shapes like this such that the next one will have the peak at this point where this is 0. And similarly, the next one will have peak here, peak here, peak here. So at wherever the carrier has a peak, every other carrier has a null. Okay? Huh?
Because they must
That's to make them orthogonal. That's what makes them orthogonal. Okay? Orthogonal means that the spacing between the carriers is exactly 1 upon t in the frequency domain, where t is the pulse time. Okay? So now using this OFDM, if we know the spacing, we can figure out how much bigger pulses, how many big pulses we can send without violating this orthogonality. So, you see, if you're going to send the pulses of time t, and then you have a guard interval or cyclic prefix, then you will need to have that much frequency spacing. Okay, and the frequency spacing is inversely proportional to the pulse time. All right. So so let's see. We finished everything here. Yeah. Similar marks exist, and dBr is decibel relative. dBr. So relative to this is the baseline 0, and then this is 1/100th of that and 1,000th of that. By the time you reach 4.4 gigahertz, minus 2 to plus 2.2, you should be 1,000 times in the power level, 1,000. Okay? All right. So let me just ask you about this thing. HRB transmit mask is somewhat clearer now. I mean, you have to read that paper, by the way. If you don't read this, you won't get the whole thing. But if you read that paper, then you will see this mask, and it might be clearer. But the idea is that power level is specified like this. Power distribution is specified. So when you design a device, it might be taken to a lab, and then there they will measure the power levels. If it is any outside of this, then you are not following the standard. Okay? And if nothing else, now you know what is dBr, decibel relative, and you know that how they keep decreasing the power slowly as you go out of the band. So this slide, which we are somewhat kind of finished, was that there is a relationship between time domain and frequency domain, and which is by this, is that in the frequency domain, whatever you selected as the frequency spacing becomes the symbol duration, and becomes basically the FFT period. So FFT period in this diagram, when we came time with duration, FFT period it says is 1 upon DFSC, and DFSC is 4.957 megahertz, right? So if you do 1 upon 4.957 megahertz, you get 201.73 nanosecond. Okay, that is the FFT period. That is the width of the data part, capital T. Okay, capital T. This we call capital T FFT. Now the question here asked was whether FFT period is same as FFT duration. I mean, maybe we can say that they are same, but then there is symbol duration which is different. Okay, so now what is symbol duration? The symbol is longer than T because we send a pulse and then we leave a gap. Okay, that was the guard interval. So the symbol is so long and the FFT part is so much. Now, actually we don't leave the gap. What we do is we send something anyway and hope that it will get there. If it doesn't get there, there's no big problem. But there's no point in leaving something unused. So that time is used, and we call it cyclic prefix. So cyclic prefix is basically we have some information that we compute based upon this data, and we put some of it in the front, some of it in the back. And if the symbol gets shifted, as it will, and some of that cyclic prefix will be lost, but whatever of the cyclic prefix is left over will help us reduce the error in whatever we have received. Okay, so these cyclic prefixes are the error correcting bits. Some of them are lost, some of them remain. Okay, you understand? So basically, so there's a FFT period which is 201 nanosecond, guard interval which is 1/8 of the FFT period. Now why 1/8? So again, they discuss how far this signal has to go. If it has to go very far, then of course you need a large guard interval because symbol can move a lot. If it has to go very short distance and the reflections maybe not be that much, in that case, we don't need that much of guard. Okay, we could have 1/16th guard, we could have 1/32nd guard, we could have, if it has to go very long distance, then we'll have 1/4 of the guard, of the interval as a guard. Right? So this gap is a fraction of this t. In this case, they decided that it has to be 1/8 of t. Okay, and so the total symbol duration is so much. So now when you calculate the bit rate available, you will calculate based upon this. In this duration, how many bits can you get through? Okay. All right. The key in this slide is that this time is inverse of this spacing. Okay. The narrower the spacing, larger symbol time you can send. And that comes from this diagram. By the way, if we increase t to infinity, what will happen on this side? It will be a constant function. And what will happen on this side? This will become impulse, because as you increase t, this will become narrower, and it will become an impulse. Okay? So impulse in frequency domain is unit function in the time domain and reverse as well. A impulse in the time domain is unit function in the frequency domain and vice versa. Okay. So when we study about fast Fourier transform, all of this becomes clearer, but we are not going to do that. But at least this is clear that the width of this pulse is 1/, of that. So as we increase this will become very narrow kind of power function in the frequency domain, and it will become an impulse at t equal to infinity. All right, now let's go to the coding. And we have discussed coding, and so, but just to be clear about it. So we have 3 coding. First is this one, the middle one, which is called outer block code, which is read Solomon 224.216. Okay, and there are many codes. Okay, read Solomon is just one of them. And so this code, RSN, K, this is a code which tells you that instead of 216 bits, we will send 224 bits using some formula. Okay. Similar to CRC, these bits are calculated using some polynomials. And so instead of sending 216, you send 224. So 216 becomes 224 bits. That is the first code, right? The second code is the inner code, and that is where you send, instead of you send them 2 for 1, or 3 for 2, or 6 for 5, and so on and so forth, right? And this is in addition to RS, And this particular code has two different kinds of coding here in our code. One is called equal error protection and one is called unequal error protection, UEP and EEP. Equal error protection means all bits are equally protected. So if you have a 156-bit frame, or 100, doesn't matter 128-bit frame, all the bits are equally protected. But in some cases, you may want to protect some bits more than the other. Unequal protection. And so, for example, you may want to protect a header better than the payload, right? Or in case of video in particular, in case of video, if you lose the last bit of a word, it doesn't make a difference. The color is, let's say, 9, and you make it 8, it will not make much difference. Right? So the first bit is much more important than the last bit. If you change the first bit, the color is 8 and it becomes -8, it will look odd. Right? So the first bit is more, so they use unequal error protection. With unequal error protection, some bits are protected more and some bits are protected less. So the way they calculate how to add the bits depends more on the some bits more than the other. Okay, so this is all selection, how you select the polynomials. All of these is actually done in polynomials. But anyway, so this is that. And then after everything is done, then we do the modulation, which is when we send on the air, we can use QPSK, 16 QAM, 64 QAM, and so on. Right? So there are 3 codes. If you want to call them codes, this is modulation and these 2 are the codes. And the new thing here is unequal error protection, because we have not seen this in other standards. Okay, this was designed especially for video, and the video people realized that, you know, first few bits are more important than the last few bits, so they introduced this UEP. Yeah.
So its impact on the data rate would just be by multiplying that value by the...
Right. So the thing is, if you do, let's take an example here, 2/3 EEP and 2/3 UEP. Overhead is same, but the video quality with UEP will look much better because the bits that matter are protected more. Does that answer your question? Right?
But so if you introduce a 2/3 UEP, you'd effectively be multiplying the data rate by 2/3?
Yeah. Yeah. That multiplication is already there. We have used this in the exam as well, right? And multiply by whatever overhead is there. So that we have, except that the new thing is UEP and EEP. Previously, we were all EEP so far. All right, so that ends the wireless HD. It is designed for video cable replacement. It has 3 PHYs, high rate, medium rate, and low rate. And low rate is used for discovery and multicast. Everybody speaks low rate. There is a centralized access, although there is no access point, but the coordinator issues the beacons and allocates the reserved transmission slots. And then random access time blocks are used for unallocated transfer. So this is actually RADBs. We had seen them before in 11AD, and we had called something else. They were called, in 11AD, they were called CPB. Congestion something, CPB. These were, contention-based something, contention-based access. So this is same thing as RADB here in 11 HD, sorry, in wireless HD. Okay. And channel time block CTBs are used for pre-allocated transfers. And then power save mode in device control. Actually, so we have skipped some of the details of this. I really wanted to concentrate on that parameter set because that is important to understand. and because we will be using that in later on in LTE and other places. All right, the summary of the whole chapter. 60 gigahertz, also known as millimeter wave, because as we said, 60 gigahertz is 5 millimeter. It has large bandwidth, very small antennas, so you can have lots of antennas, and you can use beamforming at very gigabit at high speeds. Then nowadays you can buy tri-band devices. So you can buy a router which has 2.4 gigahertz, 5.8 gigahertz, and 60 gigahertz. Actually, they are saying are coming, but they've already come. I mean, I checked on Amazon, you can buy a tri-band. And 1180 LAN uses PBSS central control point. So the central control point is there. That's a function which is built into some of the devices. And wireless HD was the previous leader. And in all cases, antenna alignment and tracking is required. So you need to practice the tracking first and then, do the alignment. All right, there's homework number 7. What is the EIRP of the system that transmits at 1 watt using a 10 dBi antenna? So now it is a directional 10 dBi antenna and it's sending 1 watt. So you should be able to calculate EIRP. OFDM system has to be designed using 1 gigahertz band, 5 gigahertz spacing, 5 megahertz spacing. Use subcarrier, size of FFT. Now here I have asked FFT duration, and the question was what is FFT duration? I would change that to FFT, whatever we used before, interval. What was it? Period. Because then we will just leave it FFT period, and symbol duration, it would include FFT period plus the cyclic prefix, and then the data bit rate using all these codes. 3/4 rate inner code, and unless it's specified, it is always assumed EEP. In this case, I didn't say EEP or UEP, so it is EEP, equal error rate protection. Any questions about this homework? None? Then here is the reading list. There are 2 books, a lot of stuff on Wikipedia. There is IEEE standard, ECMA standards, and so on. But anyway, I think that's the end.